Alrighty, so today, as I said, we're going to be finishing up the atomic structure, which is topic 2, the SL level, and then later this week, the HL students will be kind of continuing, and the SL students, you guys will be doing something a little different. But for today, this last part of the SL for topic 2, it has to do with what we call the electromagnetic spectrum. Okay, so most of this was covered in the notes that you got, the videos that you guys had on Canvas, but I'm going to quickly kind of go through and just kind of hit the high points, just to clarify anything, and then we're going to look at some practice questions after this. So the electromagnetic spectrum, as it says here, it's the range of wavelengths or frequencies of electromagnetic radiation. So it includes visible light, which is really visible light's just this tiny little portion right here in the middle. But it includes all of the different wavelengths of light that we can't see with our eyes as humans, okay? So when you're thinking about this, like all of these are waves of light, it's just we can only see this little section right here in the middle. So that's the section that we call visible light. But the other sections, we need to be aware of kind of their names and sort of the order that they go in and how they're related in terms of energy, wavelength, and frequency, okay? And so if we look at this little graph, okay, or this little chart, we have gamma rays, we have X-rays, and then we have ultraviolet waves. And then after that, here, that's in the middle here, this is where the visible light comes in, which they kind of expanded down here so that you could see all the colors, because there's a lot of different colors, but they're in that really tiny section. And so usually on a lot of charts like this, you'll see the visible light area expanded so that they can show you in a little bit more detail the wavelengths of the visible light colors. And then on the other side, we have infrared, microwaves, and radio waves, okay? Now, what you need to be aware of on here is you need to be aware of where is the, wavelength increasing, where is the energy increasing, and where is the frequency increasing or decreasing, either way. What I don't want you to say, I don't want you to say, oh, it increases going to the left or the right, or it decreases going to the left or the right. The reason I don't want you to use left and right is because the chart might not look like this. They could reverse it. They could flip it to where the gamma rays were over here on the right and the radio waves were on the left. They could flip it, kind of mirror image. So you want to make sure that you are not relying on remembering if something's on the left or the right. You want to make sure that you know the order of them and which ones have, which types of the radiation have the high energy or the low energy, or the shorter long wavelengths, etc. Okay, so keeping that in mind, I'm gonna clear some space off here. Okay, so keeping that in mind, what we need to know, if we look up here, it says that the wavelength is increasing in this direction. So it's pointing to the right. So what we need to understand is that means that radio waves are the longest wavelengths, okay? So radio waves are the longest wavelength and gamma rays are the shortest wavelengths, okay? And they go from, longest to shortest. So if you're asked to compare, if you were asked to compare like which has a longer wavelength, ultraviolet or microwaves, well, you would say microwaves because microwaves is closer to the radio waves, okay? If you were asked, which is the shorter wavelength, X-rays or gamma rays, you would say gamma rays because gamma rays are the shortest. There's nothing shorter than gamma rays. X-rays are pretty short, but not as short as the gamma rays, okay? The other thing on here is the energy, okay? If you notice, it's the opposite. Energy increases the other direction, so it's always the opposite of the wavelength, okay? So keeping that in mind, you also need to be able to answer questions about the energy. So for example, similar to the wavelength, if you were asked to compare, which of these types of radiation has the highest energy, you're always looking for the one that's closest to the gamma rays, because gamma rays, since they have the shortest wavelength, they have the highest energy, and radio waves are going to have the lowest energy. I'm writing, but it's not translating to y'all, so. Okay, so again, energy and wavelength are opposite. So your long wavelengths have your lowest energy, your short wavelengths have your higher energy, okay? And then the other thing on here is frequency, and it's not totally labeled on here. If you look, it's labeled right here, but there's no arrow. But frequency is going to be the same as energy. So you could just write increasing frequency, energy slash frequency, okay? And I left the C out of frequency, there it is. Because frequency and energy are gonna go in the same direction. So this side with the gamma rays will have the highest frequency, and over here with the radio waves, they'll have the lowest frequency, okay? So kind of overall, the gist that we need to know here, we need to know gamma rays are the shortest wavelength, the highest energy, and the highest frequency. We need to know radio waves are the longest wavelength and the lowest energy and lowest frequency. And then we need to know how all these other ones fit in between. So we need to know, the order of them so that we can compare them. And if we're asked about frequency, wavelength, or energy, we can correctly answer, which one's going to have higher or lower or longer or shorter. And then also kind of the same thing, we need to know within this visible light spectrum here, okay, we need to know the same thing. So for example, I need to know that like over here, the blue and the violet light, they have the shortest wavelength and the highest energy of all the visible light. And I need to know that over here, the red light, or the red visible light, they have the longest wavelengths of all the visible light colors, and then they have the lowest energy and frequency, okay? So we need to know kind of the whole thing from gamma rays to radio waves, but then within that visible spectrum from the red to the violet, we need to know kind of which ones have higher energy frequency, lower energy frequency, and which ones have longer and shorter wavelengths, because that's going to be important for later on. So the next thing here is these things called, there's a continuous spectrum, and then there's things called line spectra, and we're going to look at two different types of those. So a continuous spectrum, it's basically kind of what it sounds like. It's continuous, so it shows all the wavelengths or frequencies of visible light. So it goes all the way from red to violet or violet to red. In this case, they have the violet over here and the red over here. It could be reversed. It could be the mirror image where it could have the red over on the left side and the violet on the right side. But the thing is, they go in rainbow order, okay? And so if you don't remember from elementary school, learning your colors of light, you have red, you have orange, you have yellow. So we got red, orange, yellow, we got green, and then we have blue. And then there's one in here that everybody always forgets, and that is the indigo, and then violet, okay? So in elementary school or in art classes, a lot of things like that, they used to teach this little thing called Roy G. Biv, and it was like he was like a fake character, and that's how you remembered the order of the colors for the rainbow. So that same thing applies here. This picture is just reversed. It's got the violet first instead of the red, okay? But they go in the same order. The line spectra, there's two different kinds that we need to know about, and we need to know the differences between them and kind of how they're produced. Line spectra are produced when you have substances, a lot of times usually elements, and the light that they produce corresponds to the amount of energy, okay, because wavelength and energy are related, as we saw on that chart. And what we need to know is we need to know that continuous is going to show us all the wavelengths of light, but for a particular elements give off different colors when you burn them, okay, or when you run energy through them and excite their electrons. So it all relates to their atomic structure, because it relates to where are their electrons located in the atom, what energy levels are they on, and what energy levels do they jump up to and then fall back down to when they get excited, and then they fall back down. And so this first one here, this is an absorption line spectrum. The second one is an emission line spectrum, okay? And so the difference here, okay, And they go into more detail on this on your note videos on Canvas. But the difference is the absorption line spectrum, it's got a colored background with black lines. And wherever the black lines are, that's representing the only colors that are not absorbed by that substance or by that element. Whereas the emission line spectrum, it's got mostly a black background with colored lines, and that one represents the colors of light that are being emitted by that substance or by that element. So if you look, if I was to like put them together, okay, the absorption line spectrum and the emission line spectrum, if I were to fit them together like a puzzle, they make this continuous spectrum. Because remember, the continuous spectrum shows all the possible colors on the spectrum from red to violet. And so when an element is exposed to energy in the form of usually heat, light, electricity, things like that, that causes its electrons to get excited. They jump up to a higher energy level. And when they fall back down, that's when light is emitted. So they're going to absorb all of these wavelengths of light to jump up. But when they fall back down, they're going to emit a certain amount of energy. And when they do that, that's when we see this emission line spectrum produced. And so these wavelengths of color of light, they all come together and they show us a color that we would see with our eye. And that we can use that to identify the element, because every element is unique, okay? So this is kind of like the fingerprint of an element, and every element's different. So for things like astrophysicists or astronomers, people that work with outer space and things like that, this is how they identify, this is how they know what stars are made of or what planets are made of that are far away, because they're giving off a certain color of light. And they know based on these line spectrums that certain colors correspond to certain elements. And that's how they're able to identify what certain planets and certain stars are composed of. So how are these spectra produced? Okay, that's kind of the last part here. So the emission and the absorption spectrum, they're really similar. It just depends on which direction you're going, okay? And so a lot of times you'll see pictures of Bohr models like this, or sometimes instead of being the circular Bohr model, they will have like right here, they'll have this image right here where it's kind of like they've taken the lines of the Bohr model and they've just kind of drawn them in straight lines to make it a little easier for us to view and to work with. But you'll see they're similar because you can see that they have the energy levels labeled, okay? Like for example, this is N equals 1, that's our first energy level. Just like on the Bohr model, the first one closest to the nucleus is N equals 1. And then it goes up to N equals 6, just like this Bohr model. So it's showing us the same thing. It's just instead of drawing the circles, because we don't really need the circles for this, we kind of draw them in straight lines like this. So you will see the Bohr models, or that straight line one with the energy levels labeled all the way from 1 all the way to 6, okay? And what we know from Bohr's model is we know that an electron can only have a certain amount of energy, okay? That means its energy is quantized, okay? That means that like an electron, it can be here on this first energy level or the second one or the third one, but like it can't be anywhere in between. So like I'm not ever gonna have an electron just floating out here in between levels. Like that's not possible. So what Bohr's model says is that our energy levels, if you notice, the closer to the nucleus, those are the ones that have the lower energy, okay? Further from the nucleus have higher energy. And so Bohr's model says that electrons, they can transition between energy levels by absorbing or emitting energy. And so those keywords, absorbing and emitting, those correspond to our absorption and our emission spectrums, those lines that we just looked at. So what happens is an electron can absorb energy, and when it absorbs energy, it goes to a higher energy level. And this is usually in the form of heat, maybe electricity, okay? But what happens is it's not very stable, because remember our Aufbau principle from our electron configurations says that electrons always want to be in the lowest energy level possible, their ground state. So what happens is they'll absorb energy, jump up to a higher level, and then almost immediately they come back down to that lower level where they're usually supposed to be, because that's more stable. And so what happens is when they fall back down, that's when they emit energy. So they emit the energy as they transition, as they fall back down to the lower level. So those two bullets right there are very important. You need to know that when they absorb energy, they go up to a higher level. And when they emit energy, that's when they fall back down or they transition back down to the lower energy level, okay? Because those correspond to these absorption and emission spectra that we're going to look at in just a second. And so the energy, you can actually calculate the amount of energy. SL students will not have to do this. HL students, you will have to do this when we get to the next set of notes for the rest of atomic structure. We will be doing this, but it's not a very hard equation. It's just multiplying and dividing, okay? And so depending on if you're solving for the energy or the frequency. And so we're not going to go into a lot of detail on calculating that today because not everybody has to do that. But basically it kind of summarizes the bullet points here that electrons are found in those energy levels. They can only exist on those energy levels, not in between, but they can absorb energy or emit energy and go in between the levels from higher to lower or lower to higher, okay? So now we talk about how do we get these emission and these absorption spectrums? How are they produced? Well, they're produced kind of just like I said, where, you know, an electron will absorb some energy and it'll jump up. So this first one is showing us the emission spectrum, okay? So it's important that we note this is the emission line spectrum, okay? The emission line spectrum for the element of hydrogen, and hydrogen's really the only one that we need to know for IB, and it looks like this. It has 4 colors. It has 4 different wavelengths of light, and they're on a black background, and they converge at the higher energy. Converge means they get closer together. So if you look here, the blue and violet, indigo violet colors are all closer together than the red that's over here. So converge also means if you look at the Bohr model here, converge, if you look like the space between like the first 2 energy levels, that's a lot of space there. But if I get up here, like between 4, 5, and 6, there's not a lot of space. So the higher the energy level, the more converged they are. They're closer together. So what happens, okay? This is what the emission spectrum for hydrogen would look like for this visible light we see. So if you notice, there are 4 electron transitions, okay? And that's kind of what it's describing down here. It says the emission line spectrum above is produced when an electron emits energy and transitions to a lower energy level. And notice that it's the second energy level. They're all ending on n equals 2. That's very important, okay? Because only the ones that go to n equals 2 are going to emit visible light. If they go to a different one, it's not going to be visible. And we're going to talk about that in just a second. But what you need to know is you need to know that if we look, this red line, okay, we talked about on the spectrum that red has the lowest energy, okay, of all the visible wavelengths of light. So if you notice, the line that's red is the one that only goes from 3 to 2 because that's the least energy difference. Okay, as I go up, this one is going from 4 to 2, so it's not going to be, it's going to be a different color because it's got higher energy. And in fact, this one is kind of this light blue color. If I go to n equals from 5 to 2, again, now I have higher energy. Now it's kind of the darker blue, almost that indigo color. And then the final one goes all the way from 6 to 2. That's the largest energy difference. And so that's got the highest energy. So the color of it is going to be that violet. So the color of the lines correspond to the amount of energy, and it's the energy difference between the levels. And so the more levels you go between, the higher energy. And so your color is more likely going to be, you know, a blue or a violet if you're going between multiple levels. Whereas this first one, it was only 1 energy level. So that one's the lowest energy and it's red. The other thing that I want to point out that you can tell that this is an emission spectrum is all of the arrows are pointing down. They're all pointing towards that n equals 2. Okay, that tells me that the transition is going down. They're all going from the higher to the lower. And that's kind of what it says here, is it says that they're all going to n equals 2, okay, because they're going to a lower energy level. So the arrows are pointing downward, okay. And these last 2, I kind of already summarized these, but just basically the energy emitted corresponds to the wavelength or the frequency of the visible light. And so, as I said, the one with the lowest energy is going to be the color red, like this first one, and the one with the highest energy is going to be violet, because that's going to be the higher energy difference. And that's just what this last bullet says. It says from 3 to 2, it corresponds to red light. That's why there's a red line on the emission line spectrum above. If we look at the absorption line spectrum, okay, The absorption, the only difference is that it has the 4 black lines on a colored background. So it looks really similar. The only thing is it's missing those 4 lines because this is showing what is being absorbed. And so the key differences here are the absorption line spectrum has the 4 black lines on a colored background instead of 4 colored lines on a black background. But if you look, the picture down here on the Borman with the energy levels, it looks really similar to that other one. It's got the 4 lines with those colored wavelengths of light for the hydrogen atom. The only difference is all the arrows, if you look, they're all pointing upward because this is an absorption spectrum. So absorption spectrums, the arrows will point up. Emission spectrum, the arrows will point down, okay? Because absorption indicates that you are absorbing energy and you are going up to a higher energy level. And that's kind of what is summarizes down here. It just says the absorption is produced when an electron absorbs energy and it transitions to a higher energy level. Notice though that they all start on the second level. So they start on n equals 2 and they go up to whichever higher energy level, but it's the same colors as the emission spectrum because it's the same amount of energy. So for example, you know, the shortest one is still this red color right here because it's still going between the second and third energy levels. It's just, it's absorbing, so it's going up, okay, instead of going down like the emission spectrum. So the last thing is we need to know that there are some that we can't see. So all the 2 that we just looked at are kind of these right here. And they're the transitions where it goes down or from the second energy level. Anytime you have electron transitions that go to the second energy level for hydrogen, n equals 2, those are always going to be in the visible light spectrum. And so we saw that, you know, there's a red and there's kind of a light blue, a dark blue, and a violet, okay, because they do have higher and lower energy. Anything that goes to the other energy levels, for example, this one, they are all going to n equals 1. They're going to the first energy level. So if you look, there's a higher energy difference here in all 4 of these. And so what's got higher energy than violet, okay, because violet's the last visible light we can see. But there are some that have higher energy than that, and the higher energy would be UV radiation. So there are some electron transitions that we can't see, they're not visible, but they do exist, okay? And so what you need to know is that anytime you have a transition that goes down to the first energy level, n equals 1, those are going to be higher energy and therefore in the UV radiation area. And then anytime something goes to n equals 3, that third energy level, if you notice the differences here, they're a lot smaller. So there's less energy here. And so they're going to be lower energy than the red visible light. And what is lower energy than red on that spectrum? It was the infrared radiation. So you just need to know that if you see a diagram like this and you're asked a question, what you need to know is that any of these transitions that go to n equals 1 are going to be in the UV area. Anything in n equals 2 is going to be visible light, and it'll be specifically these 4 colors that we see here. And then anything that goes to the n equals 3 level is going to be infrared because they're going to be lower energy. And that's basically kind of the summarizing here is that electron transitions to the n equals 2 energy level are going to be visible light. N equals 3 are going to be the infrared, and n equals 1 are going to be in the UV radiation area. The longer the arrow, as it says right here, the greater the amount of energy emitted or absorbed, because remember, if the arrows are pointing down, it's emitting. If they're pointing up, it's absorbing. And then higher energy corresponds to higher frequency and shorter wavelength. Lower energy corresponds to lower frequency and longer wavelength. So what we need to know is we need to know that wavelength, which wavelength is represented by this kind of upside down Y, it's called lambda. Wavelength is represented by that letter. Wavelength is inverse to energy and frequency, okay? And we need to know that energy and frequency, energy is directly related to frequency. So energy and frequency are directly related, meaning that they both increase or decrease the same direction. But wavelength is inverse to both of them. So inversely proportional, meaning that as the wavelength gets longer, the frequency and energy will get lower, okay, or vice versa. All right, so we're going to switch over and look at a few practice problems before we leave today. So let me, okay. Share screen again. Okay, so we're looking at some practice problems. So we're going to look at some that are directly from what we talked about today, and then we'll look at a few that are from atomic structure stuff from before we went on break. So this first one we're going to look at is this one right here. It says number 10, okay? And it says, which electron transition emits radiation of the longest wavelength, okay? So there's a couple things here, okay? We need to look at the direction of the arrows, okay? Which ones, if the arrows are pointing up or down, which one is showing us emission? What did we just talk about?
The ones going down.
Right. So the key here is that if we just know that the question says emits, we can already eliminate B and D because they're not emitting, they're absorbing. Okay, so that's one key thing. That's why it's important that you know that the direction the arrow points is important because one's absorbing and one's emitting. So B and D should be out like right away because the question's asking about emitting. Okay, that at least gets us down to A and C because they're both pointing down. So then we need to look at, okay, they're asking for the longest wavelength. So this is where we have to know how wavelength and energy are related. Because if it's the longest wavelength, is that going to be high energy or low energy?
Low energy.
Right. So because they're inverse. Thank you, Javon. So long wavelength means that we're looking for the lowest energy change, right? So between A and C, which one do we think is going to be lower energy?
Maybe C.
Okay, well, let's check. Let me put the key up. Let's see. Correct. It is C. So it's C because one of the last things we just looked at was the fact that it said the longer the arrow, the more energy change, or there are bigger energy changes going on. So from for letter A, that arrow is definitely longer than C. So C is going to be the lowest energy difference and therefore the longest wavelength, and it's emitting because it's pointing down. So what happens is a lot of people, they only think about the length of the arrow, so they might accidentally pick D because they're like, oh, that's the shortest arrow, so that's the lowest energy, so that's got to be the longest wavelength. And they don't pay attention to this word emits in the question. Okay. Let me find another one. Let's see. Okay, let's look at 12 here. Which is correct for the line emission spectrum for hydrogen? So they've got these labeled here, MNOPQR. So if you look, it's kind of like they took that diagram and they turned it sideways almost, this diagram. So instead of N equals 1, at the bottom and going up, it's like they've turned it sideways. So it's kind of like M is the first level, N is level 2, and then O is level 3, and then P is 4, Q is 5, and R is 6. So the picture's kind of turned sideways on this one, so that's a little weird. But it says, which is correct? So the first one says line M has higher energy than line N. So do we think that that is correct?
No.
No, because remember the ones that are closer to the nucleus, which would be this one, those are going to be lowest energy. So A is not it. B says line N has a lower frequency than line M. What do we think about B?
No.
No, because remember, as we go up, the energy increases and frequency always goes the same as energy. So the frequency will go up as well as you go up. C, line M has a longer wavelength than line N.
Yes.
That one is the correct one. Why is that one correct, Javon?
Because it's farther away and it's closer to the nucleus, isn't it?
Yeah, exactly. It's closer to the nucleus, which means lower energy, and energy and wavelength are opposite. They're inverse. So it should be C. Yep, it is C. And then D, just to check D, it says lines converge at lower energy. That's not true. That's the opposite. So up here where the higher energy is, that's where the lines converge. Okay. Let's see if I find one more that we can answer about this one. Oh, okay. Let's look at 17. Ultraviolet radiation has a shorter wavelength than infrared radiation. How does the frequency and energy of UV radiation compare with infrared? So this is knowing those relationships between wavelength, frequency, and energy that I just talked about. So it tells us UV radiation is shorter wavelength than infrared. So you know, even if you don't remember that, they tell you here in the question. So now you just need to know, okay, are they going to have a higher or lower frequency and energy based on that wavelength description?
You're gonna have a higher energy.
Higher energy, and then what about frequency?
It's gonna be higher too.
Exactly. So frequency and energy, they go the same direction. So it should be A. Yes, it is A. All right, so let's take a look. Well, let's look at a couple that are from our stuff from before break. So let's look at here at number 1. It says, what shows the number of subatomic particles in this ion? And it's P, that's the element phosphorus. And then they've given us the mass number up here at the top is 31. Now they didn't write the atomic number because we do have a periodic table that we can look that up. So sometimes on the symbols, they'll leave the atomic number off because they know that you can just look it up on a periodic table as long as you know that it's P for phosphorus. So phosphorus element with the symbol P, if you look at a periodic table, its atomic number is 15. So the number down here that would be down here in the bottom right would be a 15. So from that, we need to figure out how many protons, neutrons, and electrons this ion has. So if I know the atomic number is 15, then that means that's the number of protons. So if I look up phosphorus on the periodic table, I can already eliminate C and D because they don't have 15 for the protons. So then I'm down to A and B. And if you look, the neutrons are the same, so I don't really need to check them because that's not going to make a difference. I need to look at the electrons. Okay. So based on how this symbol is written, do you guys think it's A or do you think it's B?
A.
Why is it A?
Because if it has 15 protons, that means that's the atomic number, and then you subtract that from 31, and then you get 16. And then it's a -3, so it would have to have 3 more electrons and protons.
Exactly. Awesome. So I'm glad that you remember this. But yes, so because it's a -3, that means it gained electrons. So some of us, I noticed on our practice from before the break, we were still confusing the gaining and losing of the electrons. So remember, if the charge is negative, that means it gained that number of electrons. So that means the electrons are going to be higher than the protons. So what they're doing here is they're checking that concept, because if you notice, the protons are both 15 and the neutrons are both 16. The only difference on A and B is the electrons. So they're checking to see, do you know that a negative charge means that there's going to be more electrons and not less electrons? Because a lot of people will pick B if they don't remember that concept. Okay. Oh, here's one that's related to today. Well, I don't want to do another one. Let's do, that's the same as what we just did. Let's see if we can find something different. Oh, okay. Here's number 5. Number 5, this is an electron configuration. So this is for the element chromium, which is Cr on the periodic table. Now, they've given us 3 of them that are kind of the shorthand and one that's kind of the regular long. It doesn't matter. I mean, we can do it short or long as long as it's the correct way. So if we do the shortcut for chromium, it's Cr, so it's in the 4th period, 4th row. So the element, the noble gas on the end of the 3rd row is argon. So already I should be able to eliminate A because it's got the wrong noble gas at the beginning. So if it's going to be the shorthand for chromium, it has to be Ar because that is the noble gas. That's at the end of the third period before you get to chromium. So A is out because of that. What do we think about B, C, and D though? Any thoughts? Do we remember this from before the break? I know this is a little tricky.
Oh, D.
You think it's D? Okay, so I know it's not B. Why do I know it's not B? Like, because that's pretty obvious. I can eliminate D.
I don't think it can stop at 3D3.
Well, it could stop there, like, but the thing is, there's always 4s before 3D. So, and you are correct. Chromium would not be 3. It would end with it would be all the way to 4, right? So, it is D. The reason it's D and not C, because a lot of people would pick C. The reason it's not C is because this chromium was one of those 2 exceptions that we talked about, where it's actually more stable for the 4s to give one of its electrons to the 3D and make all of them be half full. So you have 1 electron in the 4s, and then you have 1 electron in each of the orbitals of 3D. And so that's why D is correct, because C is not following that exception that we talked about. C is what it would look like if it was following all the rules, but chromium is one of the ones like copper that we talked about that it does not follow the rules. Okay, I like this one. Let's do number 6. In which set do all of the species contain more electrons than neutrons? So this is kind of like a higher level one, because you got to figure out the number of electrons and neutrons for all of them, and then figure out which one has all of them have more electrons than neutrons. So this one is one that might take a minute, because you're going to have to do each answer choice, and each answer choice has 3 things that you have to look at. So they all have nitrogen, oxygen, and carbon. So I only need to look up 3 atomic numbers from the periodic table. Nitrogen is 7, oxygen's 8, and carbon is 6. So we got a 7. So all the N's would have a 7 on the bottom left, all the O's would have an 8, and all the C's would have a 6. And the reason that's important for that is because we need that to help us figure out the neutrons and the electrons. So if nitrogen has 7, for the neutrons, I would do 14 minus 7. So all of the nitrogens would have 7 neutrons, right? Because they're all 14 minus 7. All the oxygens would be 16 minus 8. So they would all have 8 neutrons. And then all the carbons, they're all 11 for the mass. So 11 minus 6, they would all have 5 for the neutrons. So again, for the neutrons, the nitrogens are 7, the oxygens are 8, the carbons are 5, and that's just from subtracting mass number minus that atomic number, okay? For the electrons, on answer choice A, they're all going to be the same as the protons. So for this one, there'd be 7, 8, and 5. So on that, 7, 8, and 6. So A is not going to be it, because on those 2, for nitrogen, oxygen, the protons, the electrons and neutrons are actually the same, okay? And actually for B, they're going to be the same as well, because there's no charge on those, right? So on B, the nitrogen has 7 neutrons because we subtracted, and it's also got 7 electrons because there's no charge. So it can't be A or B. So then that leaves us with C and D. And if we look on, the only difference is that D, the carbon has a charge, on C it doesn't, okay? So really, we probably don't even really need to check the nitrogen and oxygen, because they're gonna be the same on both of these answer choices. So really, if we just wanna save time, just look at the carbon. If we look here, so there was 11 minus 6, so there were 5 neutrons, but since there's no charge, that would mean it would be 6 electrons. So it can't be C because, other way around. It probably is C, okay, because that one does have more electrons than neutrons for the carbon. If we look at D for the carbon, it would be 5 for the neutrons if we subtract, but then there's a charge of positive 4. So that means it's lost 4 electrons. So that means that instead of 6, it's only going to have 2. So D, it can't be D, because C, the carbon, does not have more electrons than neutrons. So it should be C. Yes, that is correct. So kind of to save time on there, really, if you looked at A and B and looked at the fact that the nitrogens and oxygens didn't have charges, there's no way that they have more neutrons than electrons. And then when you compare C and D, again, to save time, the nitrogen and oxygens are written the same. So don't check those. just check this one that's different, because that's going to be the only difference between those answer choices. And so even though we only checked carbon, because the nitrogen and oxygen are the same, we can kind of assume that, you know, that's going to be what makes the answer different, is the carbon on that last one. Oh, okay, here's a good one. This is from today. Which electron transition, oh, we're about to be out of time. Emits radiation with the longest wavelength. So emitting means we're going from the higher level to the lower level. So that means that B is out, because that's going from low to high. And then longest wavelength would be lowest energy difference. And that's from 3 to 2, because they're closer together. All right, guys, our bell just rang, so I'm going to go ahead and stop. And you guys have your note check that you need to do.